Okay, so let's start. Problem 1 for today is called merge sorted arrays. The problem statement says that you are given two integer arrays, nums1 and nums2, sorted in non-decreasing order, and two integers m and n representing the number of elements in nums1 and nums2 respectively. Merge nums1 and nums2 into a single array sorted in non-decreasing order. So what they are saying is that two arrays in non-decreasing order. That is basically in ascending order, but not strictly ascending. So suppose 1, 2, 2, 3, 4, 4. Basically in an ascending order, but it's not that the next element must be strictly greater than the previous element. It can be the same too. The final sorted array should not be returned. Instead, it should be stored inside the array nums1. So nums1 has to be modified, and it basically prompts us to not create an extra array, to use O of 1 space complexity. So before we move on to all of that complications, let's just think about the naive approach of how we would approach this problem. Just looking at the first two lines of the problem statement, thinking of what we can do. If we had no other constraints, we weren't thinking about optimization, how would we solve this problem? So this problem could easily be solved by creating a new array of size m plus n, where m is the size of nums1 and n is the size of nums2, and storing the m elements of nums1 and n elements of nums2 into that array, sorting it, and then we could replace nums1's elements by that sorted array, and that would of course give us a correct answer. That's well and good, but it has a extra space complexity of big O of n. That is, we use an extra array of size m plus n, where m is the number of elements in nums1, of course, and n in nums2, and that is inefficient. Also, the sorting of such a large array takes quite a bit of time. The total time complexity of that code would also be m plus n log of m plus n, which is inefficient, and we can certainly do better. So let's see how we can do better. We can do better by making use of the fact that the two arrays are in ascending order. That means we do not need to sort them together. We can make some modifications to our swapping and sorting, and thus reduce the number of operations required. So of course, notice that nums1 has its own n m elements, and it has an additional n zeros, which are to be ignored at the start. We need to basically put in the additional n elements from nums2 into that in a sorted manner. So how can we approach this problem in an optimal way? How would we go about doing that? A way of doing that would probably be uh, to realize that these three elements have to be the not the three, maybe it would be the last n elements. All the zeros will have to be replaced by the largest n elements, n being the number of elements in nums2. So that will be the largest n elements of the array. So we can divide this problem into two subparts. First, getting those the n largest elements, and subpart 2, combining them into nums1, that is placing them from index m to index n. So how would we go about doing that? So first we need to of course get them, and it is better to store them in place in nums2 only. There's no need of creating an extra array. And I think if we scroll down here, they ask, okay, they haven't mentioned any space complexity, but if you are giving a coding interview, the interviewer will expect an algorithm which runs optimally in times of both time and space. So it's better if we make the replacement in nums2 itself. So how can we go about doing that? For this, we can use a two-pointer approach. So notice that we want nums2 to contain the greatest number of elements, right? The greatest elements of the combination of nums1 and nums2. So we will, of course, the logical approach will be to start removing its smaller elements and swapping them with large elements from nums1. So we can create two pointers. The first pointer, let me just draw to give you a better explanation. The first pointer, let it be called R. Let it point to element or the last element of nums1. The last element of nums1 will of course be the greatest element in nums1. Notice it's sorted in ascending order. And we'll have a pointer L pointing to the first element, that is the smallest element of nums2. And now we do want the largest elements part of num2. So we'll keep on swapping until the element we are currently at in nums2 is greater than the element we are currently at in nums1. Of course, this is not the case right now. So we will swap 3 and 2. So 3 and 2 get swapped. And my pointer will now point to 5 and 2. And this does not satisfy my condition. What is the condition again? The condition is that the element in nums2 should be smaller than the elements in num1. Then only we'll swap, right? Because we want the largest elements in nums2. The only way we will swap is if we can get a larger element. That means we are replacing a small element in nums2 with a larger element in nums1. So of course, this is not the case anymore. So we won't swap, and at the end, our array will look like this. Just a second, let me make some edits over here, and you'll get an idea. Okay, just a second. Here, this will be 3 because I swap it over here, and this will become 2. Now notice this is exactly what I want. nums2 has the 3 largest elements or the n largest elements. I'm saying n as 3 because of course in the example test case they're given n as 3. But over here I'll have my m smallest elements. This case is a very, very convenient example test case. It might lead you to get wrong solutions because in this test case, notice we already have it in a sorted order. This is already in an ascending order. This is already in an ascending order. And it looks like we can directly replace the last n elements of nums1 with nums2. But this will not always be the case. Sometimes we might end up with a case where, suppose if nums1 was originally 1, 2, 3, right? And this was 2, 5, 6. Suppose I had 1 to 7 in nums1. What would happen now if I replaced as in swapped? This would become 2. This would become 7. And now if I directly placed in my elements in nums1, this would not work, right? 1, 2, 2, 7, 5, 6. This is clearly not in ascending order. And so it is not a valid solution. So sorting must be applied individually to each of the arrays over here also. So that's what the basic algorithm for this problem is. Swap elements until the current element we are at in nums2 is greater than the current element we are at in nums1 using a 2-pointer approach. And then we'll individually sort each array. We'll sort nums1, we'll sort nums2. Okay, if we do that over here, this will become 5, 6, 7. All right. And we can replace this 5, 6, 7 in nums1, making it 1, 2, 2, 5, 6, 7. And this is our answer. So let me just take a look at the code. Okay, before I take a look at the code, I do not know if anyone ran across that question or not. If I am sorting in my first approach as well as my second approach, what is the difference? Why not just use the first approach? So that can be explained by time complexity. In my first approach, what was the first approach? The first approach was combine both the arrays first and then just normally run a sort in Python and C++. It's just 2 or 3 lines of code. Why not just use that? Over here, I'm telling you, okay, you have to sort 2 arrays individually and all. Why not just do it once? what is the downside to doing that? Well, the downside to doing that, of course, is the time complexity will be m plus n log m plus n in that scenario. And in the case that in the solution I just explained to you, it will be m log m plus n log n. What is m? What is n? M is the number of elements in nums 1. N is the number of elements in nums 2. And can anyone tell me which will be bigger, which will be smaller? Of course, this is in brackets. So clearly, this is smaller. It might not look like that much of a difference to you, but it makes a huge difference actually. And that's why it is better to use this approach. If you are going for any coding interview and if you give the first approach, the interviewer will surely ask you to do better. So you can tell him the optimal approach where we make use of the two pointer method to swap elements from nums1 and nums2 until we are satisfied. Then we sort them individually, and then we add the elements of nums2 back into nums1. All right. So let's just run over the code. It is doing exactly what I told you. The merge function with nums1 and nums2 int m and n. I've declared the right pointer to m minus 1. M minus 1 being the last index of the element. Over here, for example, I'll point to element 3. And L will be 0. So L points to 2. And the while loop conditions, as I said, nums1 are greater than nums2L. So nums1 are. So at the start will be this element is greater than nums2L, this element. We'll keep swapping again and again. I want the n largest elements in nums2. That's why this is my condition. And I simply cannot put this condition alone because I'm decrementing R, incrementing L. I have to check my array bounds as well, right? If these conditions were not there, I would run into a segmentation fault and my code would break. So this is basically just checking, okay, is my right pointer in bounds? Is my left pointer in bounds? It is. And by the time it is, I will keep running this while loop. L plus plus, R minus minus. This is just a debugging statement. That's it. Swap. That's basically self-explanatory, a literal implementation of what I just explained. I sort two elements using the STL function. A neat trick in the STL is that you do not necessarily need to sort the entire array. I am telling the compiler, okay, just sort nums1 from nums1.begin. That means from the start of nums1 to m more elements because the size of nums1 is m. Okay, so sort from here from nums1 to nums1 plus m elements. Why not the entire thing? Because at the start we have zeros, right? If I start sorting with zeros, these zeros will obviously go to the start, and I'll be replacing my 1, 2, 3 with my 2, 5, 6, which will lead to an error. And this for loop is the second part of the problem I told you. Simply replacing the n largest elements I got with the last n positions in num1. And notice I am not returning anything because the function does not need me to return anything. I am simply modifying my input vector nums1 and this passes. And about the time complexity thing I told you, I think I can show it to you also what the difference is. Okay, just a second. Yeah, this was the original solution I submitted. As I told you, just sorting the whole array at once. You can see that it beats only 21% of the solutions, only 21%. And the solution I just explained to you, it beats 100%. That big of a difference. You might not think 0 and 5 milliseconds makes much of a difference, but on inputs which are larger and larger on scale, it would surely matter a lot. So that was the explanation for problem 1. Does anyone have any doubts? Okay, so then yeah. Okay, so then I'll move on to problem 2. Problem 2 for today is find the duplicate number. Find the duplicate number is a problem that looks very, very easy on first glance, and it would probably be a very easy problem if the constraints weren't this high, 10 raised to 5. So before that, let's just take a look at the problem statement. Given an array of integer nums containing n plus 1 integers, where each integer is in the range 1 to n inclusive. There is only one repeated number in nums, and we have to find this repeated number and return it. So an array of size n plus 1, it can contain elements from 1 to n, and there is one and only one number which is being repeated. So I have to find this number and I have to return it. What is the first thought that comes to your mind? The first solution to this problem? It would of course be running a nested for loop. For let me just take example 1. I'll initialize I to 0. I'll initialize j to I plus 1, and I'll check if v of I equals to v of j, for example. Okay, it is not. Then I'll move on to 3. Then I'll check for 3. Is it being repeated? It isn't. So for 4, I'll check. Then I'll reach 2. And then I'll notice, okay, it's being repeated for 2. This would work, but it would give you a time limit exceeded. 10 raised to 5 does not work for an O of n square algorithm. The algorithm I just described is O of n square, that is time complexity, worst case time complexity. It would go through n square operations with the input size being n. And since n is 10 raised to 5, it would take 10 raised to 10 operations. And a fun fact, an average compiler can perform 10 raised to 8 operations in a second. So this would take approximately 100 seconds to run, to execute, which should give you a time limit exceeded. Normally these problems have a range of maybe a second or two for each test case. So yeah, wouldn't work, can't do it. So let's understand what we need to do over here. What approach will we take over here? And how can we find? So the main observation to make in this problem is what? It is to see that for a particular element, there will be that many times, that many elements less than or equal to it in the array if it is not being repeated. What do I mean by that statement? It sounds very wordy, and I'm pretty sure a lot of you would not have understood it on the first attempt. So let me just tell you. In this array, how many elements are less than or equal to 1? Only 1, right? So that's 1. What about 2? There are 3 elements less than or equal to 2. What about 3? There are 4 elements less than or equal to 3. And what about 4? There are 5 elements less than or equal to 3. So notice that at the repeated number and after the repeated number, the number of elements less than or equal to that number are more than the element itself. So what if my array was 1, 2, 3, 4, 4, 4, 5. For example, it was this. Number of elements which are less than or equal to 1, it's 1. Number of elements less than or equal to 2, 2. Number of elements less than or equal to 3, 3. Number of elements less than or equal to 4, that's 6. And number of elements less than or equal to 5, that's 7. So notice that the first position where the number of elements are less than or equal to the current number is our answer. So at 4 we got 7, right? 7 elements less than or equal to 4. So that is the first position where a condition is not satisfied. So we must return 4. So of course we can try checking that is a valid solution, right? That is a valid algorithm. We can just check for each for which is the first element. We will run across elements which are more in count than the element itself. But how will we do this? What approach will we use for this? Can we simply check it out for each element? So can I run a check for 1, then I'll check for 2, I'll check for 3, for 4, for 5. Can I do that? I again cannot do that for the same reason as the first solution. it is big O of n square, because for each of the n numbers, I am iterating through an array of size n, right? So that is again big O of n square. It would give me a time limit exceeded. So how can we still make use of this logic while reducing the time complexity so we pass our test case? For that, we use binary search. Binary search will save our solution, make this logic very, very easy to implement. Like not easy to implement, but yeah, it will make a solution viable. So what is binary search? I'm sure a lot of you might already know what binary search is. So I'll still explain it. I'll go over it. Suppose I want to guess which number is chosen between 1 to 10, and I'm only allowed to know if my guess is higher or lower than or equal to that current number. If I was doing a linear search, how would I perform? Suppose my number is 8. So what would I do? I'd check, I'd ask if the number is 0. No. So okay, is your number 1? No. 2, 3, 4, 5, 6, 7, 8. Okay, I'd go on. I finally reach 8 and I found out yes, that my number is 8. This is O of n, right? What if my number was 10? Then I would have to go through all 10 elements to find out that, yeah, the element is 10 and it exists in the array. What if it was 100,000? Then I have to perform 1,000 operations, 100 operations, depending. If there were n elements, in the worst case, I would have to perform n operations. Time complexity O of n. But we can do this in a better way. That we can do by using binary search. Binary search is an algorithm which keeps cutting our search space in half every time. So how will we do that? Let me initialize a pointer to low, which is currently at the start of the search space, high, which is currently at the end of the search space, and mid, which is currently at the middle of our search space. So I will first ask the user, is your element 5? If not, is it greater or smaller? Of course, the element we want to find is 8, right? It is greater than 5. So if our element is greater than 5, do we really need to check 0, 1, 2, 3, 4? If it's greater than 5, it'll be greater than 4, 3, 2, 1. So no need to check all of this, right? So we can basically eliminate all these 5 elements. Notice we are cutting our array into half. Normally, to reach this point in linear search, we would have to perform 5 operations. Then we would realize that no, it's not over here, move on ahead. But over here in one operation only, we are doing this. So of course, let me just move my pointers. Now that I've cut off everything, I've cut off till 5, right? I'll move my low pointer to mid plus 1 because my element is greater than than my mid. So I'll move my low to 6, my high remains at 10, and I'll calculate a new mid. Okay, it's 8. Now, look at this. I found it in 2 operations only. So what is binary search? I set low to the start of my search space, high to the end of my search space, and I set mid to the average of low and high. Then I ask the user if mid is greater than the element I want or smaller than the element I want or equal. If it's equal, we simply return that element. If it's lower, then we'll move if it's higher, then we'll move low to mid plus 1. That means we are basically eliminating all the elements from the original low to mid. We know it's not in that search space. Discard it. Move low to mid plus 1. Now our new search space is reduced in half and we perform the same operation. Okay, what if the element was higher? Suppose the element over here we wanted to find was not 8 but was 7. Then what would we do? So we are currently at 8, right? But 8 is larger than the element we want. So then we'd move high to mid minus 1. So just a second. Yeah, so what would happen was that this part would be discarded. And in the first step only, all of this was discarded. So my low is over here. My high is over here. My mid will be either 6 or 7, depending on how you implement your binary search. And so either in 3 or 4 operations, I will find my value. And what is this 3 or 4 value? Where did I get it from? This is basically log to the base 2 of n. So log to the base 2 of n is something around 3 point something, right? So basically between 3 and 4 operations we will take to find our value in binary search. In the worst case, if we are lucky, then maybe the first operation. But in the worst case, 4 operations. So notice that for linear search, it would have taken us 10 operations in the worst case. In binary search, just 4. The time complexity of this is big O of log n. This is way, way faster than O of n. So we can make use of this. Over here, our search space is what? It's 0 to n. It's 1 to n, right? Because the element which is repeating will be between 1 to n. It is mentioned in the question, each integer is in the range 1 to n. So now instead of checking every element from 1 to n, we'll apply binary search. And it's implemented exactly in the way I explained it to you. I've set my lower boundary to 0. I could set it to 1, 2 if I'd like. Normally you set it to 0, set it to 0 over here. High is num size minus 1. Why num size minus 1? Because the size is n plus 1 and n plus 1 minus 1 is n. So that is the higher boundary I need to search, right? So low is 0, high is n. And my answer, basically my answer stores the answer I want to find. So int mid equals to low plus high plus divide by 2, basically taking the center element of the search space. As I explained in the example I gave you, 0 was my low, 10 was my high, so mid would be 5. Similarly over here, mid would be n plus 1 by 2, for example. And I'll implement the logic I explained to you before, right? The one where I have to find the first element where the number of elements less than or equal to that element is greater than that element itself. I know it's a mouthful. I'll just go over it once again. Over here, 1 is repeated on number of elements less than or equal to 1 is 1. Number of elements less than or equal to 2 is 3. For 3 it'll be 4, for 4 it'll be 5. So 2 is the first element where the number of numbers less than or equal to it are greater than 2, right? So that is the element we want to find. So to do that, we'll have to run a for loop. For this is basically int I equals to 0, I is the number size. This is a for each loop, which is very handy to write. I'm counting the number of elements less than or equal to mid. If that count is greater than mid, that means my condition is satisfied. I know that my answer will be is either this or it is lower than this element, right? So I set my answer to mid right now, and I reduce my search space. I eliminate the right hand side. So if my answer exists, it'll be either this or to the left of this. All right. So that's what I do. And if this condition is not satisfied, then I'll do low equals to mid plus 1. That means, of course, if my this element is also not satisfying, suppose the element was 3 and 3 is not satisfying the condition, I prove to you all that 1 and 2 also would not satisfy this condition, right? So I can discard 1 and 2 along with it, and I'll set my new lower limit to mid plus 1. And this keeps on running until low is less than or equal to high. That means as soon as my lower boundary exceeds my higher boundary, I will stop my binary search. So when my lower boundary exceeds the higher boundary, I need to stop because I've exceeded my search space. I have searched everything I needed to search, and my answer is currently stored in ans. And I just return that element. So that was the binary search approach to this. There could have been better solutions to this problem too, but they have given us additional constraints over here that we must not modify the array and we must use only constant extra space. So that was my solution to the problem, find the duplicate number. It used binary search, which is a very, very important concept used in a lot of problems. Does anyone have any doubts?
Yeah. So, like, what if I don't understand? Like, what if I don't get, like, we have to use binary search? Like, I don't
Uh,
get it at an instant. How am I going to solve the problem then?
If you do not realize that you have to use binary search, how can you solve the problem? That's what you're asking.
Yeah.
So yeah, like that's the thing. You get it with practice only. Now that you solve this problem, maybe when you come across a similar problem, you will realize ki, ha, I've seen this kind of problem before. I need to use binary search. And one major hint that I can give you is that you can look at the constraints. Look at the constraints over here. It says n should be less than or equal to 10 raised to 5, right? That means I cannot use uh, an O of n square algorithm. It either has to be O of n or it has to be O of n log n. So what is an n log n algorithm you can think of? It's either sorting or searching or binary search. So this is a very big clue, the constraint itself. And technically, you can use binary search when your function is monotonic. So either it's strictly increasing or strictly decreasing. In this problem, I could use binary search because I knew that, okay, if my condition is not satisfied for 4, then it won't be satisfied for 1 or 2 or 3 either. That means I do not have to check for them individually. If my 4 is not satisfying the condition, then 1, 2, 3 won't satisfy it either. It's like that example I gave you for binary search only. If my element is greater than 5, it will be greater than 4 also, greater than 3 also, greater than 2 also. No need to check, right? So that's the thing. And if it's monotonic, so if my solution exists in the exists for a particular element, for all elements lower than it also it will exist, or in this case for all elements higher than it also it will exist, or for all elements lower than it won't exist. So that is the logic of binary search. You will get this more by
Can
practicing
you
only.
explain it with the run? Take an example. Try running it.
Okay, so is this example fine? Example 2, we discussed example 1,
No, ये
so
तो
let's
मतलब ये तो इसका साइज थोड़ा छोटा है तो वैसे ही इनलाइज हो रहा है थोड़ा मतलब 6-7 एलिमेंट होते हैं
okay,
इसके अंदर.
sure. Give me a test case and we'll do it for that. Uh, so n plus
2
1
1 3
element.
4 5 6 6.
Which one?
2 1 3 4
2, 1, 3,
4 5
5,
6
6,
6 7.
5, 6, 6, 7. Okay. So this has how many? This has 8 elements and it has one repeating element, that is 6, and it has elements from 1 to n. So fine, this is a valid test case. Let me just increase the font size a bit. So we can see it clearly. Okay. Yes. So what would be the approach over here? Let me take a photo of this code too and put it side by side so you can get an idea. So let me move this downward a bit. So yes, so initially my low would be 0, fine. My high would be nums.size minus 1. So let me write low equals to, let me increase the font size to 18 only. Low is 0. One sec. $18. Low is 0. High will be equals to 7, right? And I'll do int mid equals to low plus high divided by 2. So my mid equals to 3. Now I'll check for all the elements in this array, how many elements are less than or equal to 3? 2 is, 1 is, 3 is, and then none of the other elements are, right? Let me move this upwards a bit. So my count is equal to 3. Got it? So what is the case over here? Is count greater than mid? No. So low is equal to mid plus 1. So I'll set low equals to mid plus 1, which is 4. And my loop ends. Is low less than or equal to high? No, low is 4, high is 7. No, so the condition is not still being satisfied. So the loop will continue to execute. What will a mid be now? 4 plus 7 divided by 2. So that's 11 divided by 2. That is 5. So our mid is now 5. Now I'll count the number of elements which are less than or equal to 5. 2 is that 2 satisfies 1, 3, 4, 5. 6, 6, 7 does not. So my count is 5. Is count greater than mid? Count is 5, mid is 5, count is not greater than mid. Again, we'll go to the else condition. Low equals to mid plus 1. Low gets set to 6. Mid, and now again a while loop will run. Mid is 6 plus 7 by 2. So I'll 6 plus 7, so 13 divided by 2, 6, because it gets rounded down, of course, it's integer division. And now I'll count the number of elements less than or equal to 6. 2,
7.
Yeah, 7, right? So my count will be 7. So now is count greater than mid? It is.
Yes.
So I'll set my answer to what? Answer is equal to mid, which is 6. And I'll set my high to mid minus 1.
ये रीजन क्या है मतलब हाई को मिड माइनस 1 करने का कि मतलब उससे आगे वाले अब सारे मतलब वो मतलब यूज के नहीं है।
तो मैं क्या कर रहा हूँ, बाइनरी सर्च में जो है ना, मैंने नोटिस किया कि अभी 6 के लिए वैलिड है, तो मुझे पता चल गया 6 के लिए वैलिड है तो 7 के लिए भी वैलिड होगा, 8 के लिए सपोज 8 होता है तो 8 के लिए भी वैलिड होगा। हाँ, तो मुझे अभी इसके आगे तो सर्च करने की जरूरत नहीं है बिकॉज हाई बिकेम लेस देन लो, राइट। बट सपोज नहीं होता तो अभी मुझे 5 के नीचे ही सर्च करना पड़ता। मुझे पता चल गया कि अभी 5 के ऊपर सर्च करने का कोई फायदा ही नहीं है, उसमें तो हमको पता है कि सब में सैटिस्फाई होगा काउंट ग्रेटर देन मिड, इसलिए आई एम सेटिंग हाई इक्वल्स टू मिड माइनस 1।
ओके, बेसिकली हमको एरे देखनी नहीं है, जो टोटल साइज है 0 से लेके 7 तक मेरा वो था सर स्पेस 0 1 2 3 4 5 6 7, और उसके अंदर फिर उसके मिड से पूरी एरे के एलिमेंट्स कंपेयर करने थे कितने छोटे हैं। और जो पहली बार वो लेट करेगा वो मेरा एक आंसर हो सकता है।
एग्जैक्टली वही आंसर होगा मतलब वही को पहले एक ही है। हाँ, एक ही आंसर, बिकॉज क्वेश्चन में क्या बोला है, एक ही एलिमेंट रिपीट हो रहा है। तो सपोज हमारा मिड समहाउ 7 आ गया होता तो 7 भी ये कंडीशन सेटिस्फाई करता है ना, 2 1 3 4 5 6 6 7, so there are 8 elements which are less than or equal to 7, so count is greater than mid, so answer for now would be set to 7, but still binary search would continue, and then when the binary search would go to 6, no, it would find that 6 also satisfies.
अगर 7 से पहले 6 से पहले 7 आ जाता तो वो सेटिस्फाई कर सकता था शायद।
एग्जैक्टली, ये थोड़ा ज्यादा एडवांस कॉन्सेप्ट है, बट it's called a predicate function. So
predicate function जो अपना वो चेंज करता है अपनी वो false से true है, true से false।
So this is the concept of binary search. Our answer will either be the last false or the first true. So in this case our answer we need to find the first true, right? तो इसलिए मैंने इधर डाल दिया answer equals to mid. ये जब true है तब मेरा आंसर ये है. So this binary search will always give you the first true or the last false of the predicate function. तो इसलिए मैंने ऐसा किया है.
Binary search में isn't it has to be like in ascending order?
That is when we do binary search. This is binary search in binary search on answer. The elements in the array. Yeah, the elements in the array are not in ascending order, but notice what I'm trying to find is number of elements less than or equal to the current number. So let's take a look at that. For 1, only 1 element. For 2, only 2 elements. For 3, there are 3. For 4, 4. For 5, 5. For 6, there are 7. And for 7, there are 8. This is in binary search, right? This is in a sorted order, right?
So, Rahul, एक सेकंड में बोलता हूँ. Basically, what he's trying to say is कि binary, like first, some of you asked that binary search कैसे intuition लगता है. So whenever your search space is sorted, right? अगर search space sorted है या फिर तुम्हारा array sorted है, then you can think of applying binary search once. And in this question, since we're trying to find the duplicate number from 1 to n, So basically तुम्हारा जो search space है वो sorted है. It's like 1, 2, 3, 4 वो sorted search space है. So now what Ryle is trying to do is वो search space में हम pick कर रहे हैं. Suppose we took the middle element and then we check for the middle element कि वहां तक का count क्या है. So I think you get the intuition कि like binary search कैसे लगता है now.
मतलब जब आंसर या जो गिवन एरे है वो सॉर्टेड हो, या फिर जो मैं सर्च पेज दे रखा है उसमें दिख रहा है कि वो इसी के अंदर होगा, सॉर्टेड के अंदर होगा.
अगर given array sorted है then you can think more of binary search. एंड अगर तुम्हारा सर्च स्पेस सॉर्टेड है लाइक द यहाँ पे जो स्पेस दिया है 1 to n plus 1 का राइट एंड 1 to n का दिया है एंड वो हमारा सर्च स्पेस हो गया. अब ये पूरा सर्च स्पेस सॉर्टेड है, देन यू कैन अप्लाई बाइनरी सर्च ऑन आंसर बिकॉज जो आंसर है वो सॉर्टेड एरे में मिलेगा लाइक दैट. एंड इफ अगर तुम्हारा एरे सॉर्टेड है देन यू कैन अप्लाई बाइनरी सर्च. बाइनरी सर्च ऑन आंसर इज अ एक्सटेंशन ऑफ बाइनरी सर्च. लाइक एक लेवल ऊपर जाता है बाइनरी सर्च ऑन आंसर from the normal binary search. Okay.
तो बेसिकली n log n है ना कॉम्प्लेक्सिटी, क्योंकि n
Yeah,
बार जाके
yes,
log n
yes.
कर रहा है ये.
Yeah.
इस पे ज्यादा प्रैक्टिस करना है तो मैंने एक प्रॉब्लम डाला है मीट के चैट पे, बाइनरी सर्च ऑन आंसर पे एग्रेसिव काउस करके एक प्रॉब्लम है.
Aggressive cows is like the standard binary search on answer problem. Like जब सीखते हैं तो सबसे पहले यही solve करते हैं. So try that once.
Very similar to this problem, very similar code you will have to write. Just the condition to check will be different in each binary search problem. ये binary search में we were checking the number of elements less than or equal to the current number. In another problem you'll check for something else. But this while loop, while low less than equal to high, mid and all will remain the same only. So yeah, those were the two problems for today. Does anyone have any doubts? Okay, so I guess we'll end the meeting here today. Thank you all for attending. Bye bye.
Thank you. Bye bye.